Hi, welcome to 33rd session on measure theory, sixth session on LP spaces. So this will be perhaps the last if I can cover the material within about an hour, otherwise another half an hour perhaps as the last session. Okay. So we already defined LP spaces for P equal to 1, namely L1, which is a space of integrable functions, and we also defined L infinity, which is the set of essentially bounded functions. And we showed that both are norm-linear spaces. There we have the norm, and with respect to the norm, they are complete. In the technical terms of functional analysis, sorry, I was disturbed by a call. In the technical terms of functional analysis, we have shown that L1 is a Banach space. It's a complete norm-linear space. Similarly, L infinity is a norm-linear space. Then we want to define for 1 less than P less than infinity LP spaces, and we will also show that we can define a norm on them, and with respect to the norm, they are all complete. Okay, this will be the essentially what we plan to do. And the final thing which I will not dwell upon is that the density of subspaces. Whatever we are shown, the subspaces which are dense in L1, okay, they will be dense in LP also. Okay, and the proofs are essentially same except that you have to deal with the power P and 1 upon P, etc. Okay, the proof is the same. That's why I wanted the ideas to go across completely, and that's why I stuck to L1. And if I remember right, I spent a little more than 2 sessions on that, maybe 3. Okay, please go through that. Okay, so let us get started. So as we did, let X be a measure space. Okay, and fix 1 less than P less than infinity, right? Then we want to say F is in script LP of X be mu. Since X be mu is fixed, we'll simply say LP if mod F to the power P is integrable. Okay, that is same as saying integral mod F to the power P, mod F to the power P is in L1. Okay, that is if only saying integral mod F to the power P over X d mu, this is finite. Is the definition clear? For example, P equal to 2, what does that mean? This means integral mod F squared d mu should be finite. Okay, this will the reason why I chose P equal to 2 should kind of trigger some memory in you. Do you remember? Suppose my X is n and B is power set of n and mu is the counting measure, and we have seen that my L1 of n, P of n d mu is nothing other than set of an, okay, sequences such that mod an is finite. It's absolutely convergent. You can remember any f is a function from n to c or r that we can think of as a sequence. So the associated series should be absolutely convergent. We had already seen that. This is my L1, right? Therefore, what should be my L2 then? L2 simply says mod an such that summation mod an squared. Okay, remember mod f to the power p should be in L1. That means this should be finite, right? You must have seen such things in Hilbert when you studied Fourier series. Okay, always try to understand a little more than what is necessary for passing exams, then therefore you will be better off. Okay, right. Again, the contrast is if I take the sequence an equal to 1 by n, We know that an is not in L1 of n, but this is in L2 of n, right? This is from our BSc analysis on infinite series, right? Is it clear? Right. So this is just a small digression. So pause, review. Okay, let me just check screen sharing is on. Yes. Okay. So now on this, again as usual, we want to identify. Okay. That is, I have LP and modulo this, where the equivalent solution f equal to g, if only f equal to g almost everywhere. Then we will call it as LP. These are the equivalence classes. These are like we did in L1 and L2, L in infinity. Okay. Now I want to define a norm on that. Okay. Remember on L1 I call, even though most often I wrote this, I said the precise way of writing will be L1 norm of f. Similarly for L infinity, this is called the L infinity norm of f. So I would like to define LP norm of f. Right? So obvious thing may be to define, okay, because mod f squared is finite, therefore I would like to define perhaps mod f squared d mu, or mod f to the power d mu. But then there is a problem, because if I start with alpha to be a scalar, my f may be RC. Okay, then alpha f p will be mod alpha power p and mod f power p. So it's not equal to mod alpha into something, unless p equal to 1. Remember, my p is 1 less than p less than infinity. Yeah? Right. Therefore, obvious change I would like to make is define this to be integral of mod f to the power p d mu and take it to the power 1 by p. Right? This 1 by p, then remember, this is a non-negative real number. There is a unique pth root. Okay? This is the unique pth root. Okay, exactly the way you define unique square root. This is the same thing. Okay, right. This you must have learned in real analysis. I am not going to stop and prove it here. Okay. Now it's very clear norm of f of p is greater than or equal to 0. Right? And suppose is equal to 0. Right? Again, I would like to say whether it is 0 almost everywhere with respect to mu. I will not write this mu hereafter. Right? Okay. That is very clear, because if integral mod f power p for 1 by p is 0, that implies mod f power p is 0. Since this is non-negative, this implies mod f power p is 0 almost everywhere. This implies f is 0 almost everywhere. Okay. So the first condition is satisfied. Homogeneity condition is also satisfied. Homogeneity meaning norm of alpha f p is mod alpha norm of f. This is also satisfied. So what remains to be shown is triangle inequality. Right? Okay. Before we do that, let's go back. What class of functions will be in LP? Right? That's a question you can ask. Remember, the only way I can do is I just have to say whenever this is in L1. Therefore, life becomes easy. Suppose I have a step function f, which is something like ck, k equal to 1 to infinity. Right? What will be mod f to the power p? That will be simply mod ck to the power p. Okay. So this has to be in L1. Therefore, what does it mean is whenever ck is not equal to 0, mu of ek must be finite. That means, right? That means all finite, all simple functions in L1 or in LP are 1 less than equal to p less than. In fact, equal to infinity also. I am assuming this is f. Remember, my definite simple function is f takes only finite values. Therefore, none of the ck's could be infinite. Okay? Right. Now let's come back. So what we want to prove? Triangle inequality. Okay? Let us try to see even when p equal to 2, okay, right, we have the problem, right? You must remember your inner product spaces in real and linear algebra, right? So what did we do? Suppose it's a Cn or Rn, I have z dot w equal to summation zk wk bar. Just assume real, okay? Then this defines a norm of z equal to z dot z and its square root. Then you wanted to say this is this as a triangle inequality is true. Do you remember how you proved it? Triangle inequality for this norm, that is norm of z plus w is less than or equal to norm of z plus norm of w. Okay, for z w in f power n, where f is CR or, right? The important thing is this Cauchy Schwarz inequality. Right? It said that you take this modulus, this fellow will be less than or equal to norm of z into norm of w. Okay, this is the one, right? Using this Cauchy Schwarz inequality only, we proved these inner product spaces. Right? Now let's again look at how did I'm just trying to give an idea of how things work out. As usual, they may not be needed for your passing any of your exams. Okay. Suppose I have two real numbers x, y, right? We know this is less than or equal to x squared plus by 2 plus y squared by 2. That is because x minus y is whole squared is greater than or equal to 0, but that is equal to x squared plus y squared minus 2xy. Right? Therefore, this is greater than or equal to 0, and that means x squared plus y squared is greater than or equal to 2xy, and divided by 2. This is how we got it. Okay? It's analog, right? So, what I want to prove is analog. Okay? But I don't want to state it. So, the analog of Cauchy Schwarz inequality for LP spaces is called Young's inequality. Okay? I don't want to write it. In fact, in my original things, I immediately used to write what the Young's inequality is, and because it's very symmetric, so it's very easy. But then I have to assume what is meant by conjugate indices. Don't worry, we are going to define all of those things. If you have already seen, it's fine. Okay. Now the proof which I am going to indicate is trying to guess how the conjugate index comes. It tries to show that. Okay. Let us try to understand. Let us go slow. Okay. As usual, I assume that you want to learn the subject well, become a master rather than cram it for any examination. If that be the case, I think you should leave, because it will be a waste of your time. Okay. So let us look at this. My Cauchy Schwarz inequality, this one, x squared by 2, right? Look at this. and minus x squared by 2. Right? What we proved, that was xy is less than or equal to x squared by 2 plus y squared by 2. Therefore, I have something like this. I am looking at this. Right? Just for fun, please bear with me. Let me look at f of x equal to, instead of y, let me call it a b, fix y. Okay? Therefore, I can write it as bx minus x squared by 2. Right? Instead of thinking of function of two variable, f of xy, I am thinking of only as a function of one variable. I am freezing the other variable y. Just for kind of concreteness, I am just writing y equal to b so that life will be easy. Right? Then the standard way of looking at is look at maxima, minima. Yeah, this is one thing. If you have gone through my real analysis course after mean value theorem, I would have proved, I would have said that the best way to establish many inequalities is to use mean value theorem, differential calculus, and maxima minima at that kind of thing. Okay. In fact, I would have worked out in my book and also in my video lectures, I would have worked out some examples. So we are going to do that thing. Why I am repeating these things? In case you didn't learn that, okay, this is another occasion for you to learn a good principle to how to prove inequalities. Okay, so let's go back. Okay, let me look at the critical points. They are f dash of x equal to b minus x. Therefore, the critical point is x equal to b. Right? Now let's look at, I'm assuming x, b, they're all positive. I'm on this interval 0 to infinity. Okay? Right? Therefore, let me look at b, and this is my 0, this is my b. Right? Now let us look at what is f of 0. F of 0 is 0. And what is f of b? F of, because x equal to b, that is f of x at x equal to b. This is b squared minus b squared by 2. You understand that? The value at this is this. Let's go slow, don't worry. Okay. Then what is the behavior of the function? Yeah. Okay. Notice that f dash x, if x is here less than b, you can see b minus x. Okay, this is positive, right? So f dash is positive on positive or negative x. Yeah, positive, right? Therefore, it has to be increasing. So therefore, f is increasing on 0 to b. And f dash is negative on b to infinity. Therefore, f is decreasing on b to infinity. Is that clear? Right? Therefore, without even computing the second derivative, I can now we can see that f at b, that is b squared by 2, must be the maximum of bf on the interval 0 to infinity. That is, for all x, I have fx is less than or equal to f of b, that is xy minus x squared by 2 is less than or equal to b squared by 2. Right? Therefore, now b is some, I fixed, right? I fixed y to get a b. Therefore, y, it could have been anything. That means xb, sorry. That means xy is less than or equal to x squared by 2 plus y squared by 2. Because putting b equal to y, arbitrary y, therefore this. Again, remember xy are non-negative. Okay. So I gave a complicated proof which you had already seen using this. Yeah. Pause. Review. Proceed. See, the reason why I did that is I want to kind of generalize this argument for P. Okay. So I thought of P equal to 2, but very trivial thing. By looking at x minus y whole squared, we already proved it, but using calculus, I am trying to prove. Okay. This is how I do that, even though I know it will be waste of time. Okay. I keep doing it so that I at least understand. Okay. So let us go ahead. So now let 1 less than p less than infinity. Right. So what is the function I want to construct? The function I want to construct is again xy minus x to the power b by p. That is p equal to 2. What we already had, I am looking at the same thing. Yeah? Do you understand what I am doing? Now let's do the same analysis. Okay, again x, y, I am assuming they are all non-negative. So fix x, fix y, then I want to look at the critical points of x going to f of xy. Y is fixed. Okay, this is going to be y minus x to the power p minus 1. Right? So call a so that a to the power p minus 1 is y. You understand that? Yeah? A is of course non-negative. Are you following? Okay. Now again look at the picture. I have 0. I have this a where such that a to the power p minus 1 is equal to y. Right? Now if I have an x here, right? Notice that then what I have to look at x to the power p minus 1. That will be less than or equal to a to the power p minus 1. That will be less than or equal to y. Yes? Remember, I am using the fact p is greater than 1 here. Okay, we use the fact here. Okay? Therefore, this is, so f dash is positive on 0 to a, and for the same reason negative on a to infinity. Therefore, f is increasing in 0 to a and f is decreasing in a to infinity. Right? Therefore, f has a maximum at a. That is y to the power 1 by p minus 1. Yeah. Remember, p is greater than 1. Yeah. Right. Now, what is the value of f at a? Okay. That is, let me write fx at x equal to a. Therefore, I will not make any mistake. That is xy minus x to the power p by p. Right. That is, I can keep it any way. Let us assume. Let me take x is, remember this x is at a, right? Therefore, it is going to be y to the power 1 by p minus 1. X at a, that will be ay minus a to the power b by p. But a is this into y minus x to the power p, that is a to the power p. Remember, a to the power p is this fellow, y to the power p by p minus 1 by p. Yeah? Right. So this one, let us do that. Is 1 plus 1 by p minus 1. That is going to be p by p minus 1. Therefore, this is y to the power p by p minus 1 minus y to the power p by p minus 1 by p. Therefore, it is y to the power p by p minus 1 into 1 minus 1 by 1 minus p. Remember, again, p is greater than 1. Therefore, this will be positive. Right? Therefore, f has a maximum at y to the power, let me just look at y to the power p minus 1, right? Y to the power 1 by, yeah, y to the power 1 by p minus 1, and f at that point, okay, call this x, okay, or call it a. Therefore, for all fx is less than or equal to fa. Therefore, I have to find what is fa, that is y to the power p by p minus 1 by 1 minus p. Yeah, right. So let us go back. So I have x, y minus x to the power p by p is less than or equal to y to the power p by p minus 1 into 1 by 1 minus p. So notice that 1 by 1 minus p is same as p minus 1 by p, and these two are reciprocal of each other, right? So if I set q equal to this fellow 1 by 1 minus p, then I can rewrite this as, this is y to the power, I want it to be q, let me write it, okay. So let me q equal to p minus 1 by p, then it is y to the power, no, sorry, I want it to be q, so let me write it. So my q equal to p by p minus 1. Oh, that's what I did. Okay. This y to the power q into 1 by 1 minus q will be 1 by q. Are you following? So we have got xy is less than or equal to x to the power p by y to the power q by q for all xy greater than or equal to 0. So pause, review, proceed. Okay, go through this. It's very elementary as you could see, but it's fun to do that way. On the way, we also see, we introduce, given a p, we introduce a q also, right? I'll come to that in a minute. And those who had already seen p and q relation and know the technical word or jargon conjugate indices, now you see how they came. Okay? Well, given a p, how q came is very clear now. Yeah? Right. Let us do that. So, this is called Young's inequality. Before that, let me introduce a jargon. Okay, let 1 less than p define q, okay, by 1 by p plus 1 by q equal to 1. This is how one usually does. So therefore, what is q? Therefore, 1 by q is 1 minus 1 by p. That is p minus 1 by p. Therefore, q is p by p minus 1. That's what we got. Yeah. Then p and q are called conjugate indices. When I take p equal to 1, I take q equal to infinity. Then let us see 1 by p plus 1 by q is 1 plus 1 by 0, right? 1 by infinity, which is 0, therefore 1, right? So for 1 less than p less than infinity, my q is defined by p minus 1. I hope I'm right. Yeah. And when p equal to 1, I say q equal to infinity. Therefore, for 1 less than equal to p less than equal to infinity, okay, define q to be p by p minus 1. Okay, this is for 1 less than p less than infinity. Otherwise, when p equal to 1, define it to be infinity when p equal to 1, and define it to be 0 when p equal to infinity. Okay, So the ordered pair PQ defined so far are called conjugate indices. So Young's inequality says let P and 1 less than P, Q less than infinity be conjugate indices. Remember, for Young's inequality, I'm not allowing P and Q to take the extreme values on infinity. Okay, and for all x, y greater than or equal to 0, we have x, y is less than or equal to x to the power P by P, y to the power Q by Q. And also, if you go through the proof, you will also see equality holds. Okay, let's go back. When does the equality hold? Let us try to see that. If and only if I have this one. Okay, x equal to this. Okay, let's not worry about it for the time being. Okay, let's not worry about the time being, that if they are equal. X to the power P equal to y to the power Q. I hope I am right. Let's go to the proof. I have this inequality. When does the equality hold? Equality holds only at the point where the maximum is attained. Yeah. Before that, yeah. I'm sorry, I did a lot of work today before this lecture. So I should probably show my achievements. Yeah. So I did analysis, right? You did that, where the maximum is attained, etc., etc. I computed, right? I just wanted to draw pictures of such things, and I got something interesting. I just want to show it to you. Now you see that this is your bx minus p power x power p by p, where p is equal to 4 and my b is 27. Okay, you can see when I differentiate, I get 4x cubed, therefore this cancel, therefore x cubed must be equal to 27, right? Therefore x equal to 3, that should be the maximum. You can see that's a picture, maximum is attained there. I chose numbers so that things will look simpler. And look at the same thing. Instead of that, I took x cubed by 3. If I differentiate, I'm going to go to x squared, right? Therefore, I'm going to get 25. Therefore, x must be 5. You can see x equal to 5 is the maximum. But if you don't have the scales, x and y axis, you can see the picture, you would almost believe the picture is the same, right? So you can see on this interval, from here to what I call A is here 3, it increases, after that it decreases. Similarly here my A is 5. Okay, that's it. Oh, I didn't screen share, right? I'm sorry. It's a nonsense. Sorry. I'll screen share now and do that. Yeah, look at that. I will repeat. Okay. So I took my f of x equal to bx, which b is 27, and x to the power 4 by 4, therefore p is 4. If I differentiate, I'm going to get x cubed, and I'm going to x cubed must be equal to 27. I chose numbers carefully so that x equal to 3. Therefore, that should be a point of maximum. You can see that. And also we computed 0 to 3, it should be increasing, 3 to infinity should be decreasing. And a similar graph, okay, 25 times x cubed by 3, differentiate, I get x squared equal to 25, therefore x equal to 5 must be a point of maximum. You can see that. Okay, that's what I explained. Now, one more interesting thing is, if I are not given this title, if I are not given this axis, okay, scale the axis properly, these units are not visible. Okay, it looks a little steeper, otherwise I would have thought it's the same picture. Do you see that? Yeah, so that is the function. We had been dealing with that. So is that clear to you? Now what we want to do? So I got Young's inequality. Then from that, I want to say something more. Okay, I want to prove triangle inequality. Before that, I don't think I have shown my LP spaces is a vector space. LP space is a vector space, right? Then only when I want to say this is a norm makes sense. So I have to say it's a vector space. So let us do that. So let us look at the general LP. Okay, this will be a vector space. What does that mean? I have F and G here. That means mod F to the power P is integrable and mod G to the power P is integrable. Then I want to know whether F plus G mod F to the power P is integrable. Okay, this is what the question is. Right? And this, see, many of this kind of thing is actually pointwise estimates. What do I mean by that? So, I will explain by means of example. You will see every time we will be doing such thing. Okay, when I wanted to prove the alien norm is a norm, again I did the same thing. Okay, F plus G at X. Okay, I wanted to say is less than or equal to mod Fx plus mod Gx. Then I said this is less than or equal to alien norm plus alien norm. Of this, whenever the exceptional set for A is F, exceptional set for G is B, whenever X is not in A union B, then mod of X is less than or equal to this, because this essential supremum is again an essential bound. We proved it. You understand that? We needed that fact to say this here. Are you following? These are the subtle points, because of lack of time, teachers do not explain and textbook also don't write because it becomes voluminous. Okay, why this is true? Because this is an essential bound. Therefore, if X is not in A union B, X is not in A, therefore mod of X will be less than or equal to the essential bound. That essential bound here is this. Is it okay? All right. So similarly here, right? So yes, usually you get a pointwise estimate for functions and then try to say something about integral estimate. Okay, let us do that. So let us look at that. Means let me look at mod A to the B power P is what I want to say something about this. Is that clear? Yeah. So what we do is let us look at mod A, but remember mod A plus B is less than or equal to mod A plus mod B. Therefore, when I want to say this, okay, and remember P is positive, in particular greater than 1, this will be true, right? Therefore, if I get an estimate for this, it will be good. Yeah. Remember, this is what I always emphasize in analysis. When you want to estimate something, look for something bigger and say that you can estimate easily. That's what I want to do. Now, mod A is less than or equal to mod equal to, in fact, mod A to the power P and take its Pth root. Okay. There is nothing new. But interesting thing is, this will be less than or equal to mod A to the power P plus mod B to the power P to the power 1 by P, right? Yeah, in the positive thing, if X is less than Y, X to the power 1 by P will be less than Y to the power 1 by P. These are all positive. Okay, these are all basic analysis, right? And similarly, mod B is less than or equal to the same object. Therefore, mod A plus B will be less than or equal to mod A plus mod B. That will be less than or equal to, for mod A I have this estimate, mod B also I have this estimate, therefore it's a twice, right? 2 times mod A to the power P plus mod B to the power P to the power 1 by P. Therefore I want an estimate for this. That's less than or equal to mod A plus mod B to the power P. That will be less than or equal to 2 to the power P into mod A to the power P plus mod B to the power P. Pause, review. So what we got is a pointwise estimate. For 2 numbers, we got it. Now how will I do that? what we will do is take a equal to fx, b equal to gx. Remember, mod f to the power p is integrable. That means mod f is finite almost everywhere. So only for such x we will do it. Are you following? Okay, without loss of generality, I am going to assume f is finite almost, finite everywhere. So that I don't to say for only those x. Okay, are you following? Mod f, yeah, mod f to the power p is integrable. That means mod f is finite almost everywhere. Therefore, except there is an exceptional set A which is of measure 0, outside which mod f is finite. Similarly, there is an exceptional set B outside which mod g will be finite. Okay, mod g of x will be finite everywhere. There. Okay. Therefore, take A union B, throw away that set. For all x not in A union B, I will estimate. So this one I don't want to repeat, but learn this well. If somebody wants to test whether you understood what you're doing, okay, you should learn to answer. You should know how to answer. Okay. So let f g be an LP or script LP if you want. Okay. And as I said, assume without loss of generality, f and g are finite everywhere. That means it takes values only R and C. Right? Then I have mod fx plus gx is less than or equal to, what do I have? 2 to the power p into mod fx to the power p plus mod gx to the power p and whole to the power 1 by p. No, not, sorry. Sorry, this is power p. Yeah, I'm using this above. Okay. Right? Now this is true for all x and x. Right? Therefore, by using monotonicity, what do I get? I get modulus f plus g at x to the power p is less than or equal to linearity of the integral pushes these two out. Then I have linearity of the integral mod fx to the power p, right? And additivity of the integral rather to the power p, the whole thing. Okay, this is finite, therefore this is finite. Therefore we proved f plus g belong to LP. Yeah, is it okay? So it's already 43 minutes. Okay, so naturally I don't think I will be able to finish in this session, but is that clear? So we will prove that it's a norm using this one. So what do you think I have proved? Let us go. So what I have shown, similarly scalar multiple, that's very easy. If alpha is a scalar and alpha f to the power p will be mod alpha to the power p and mod f to the power p. So this is finite, therefore LP is a vector space. Okay. Then as I said, on this one, capital X B mu, these equivalence classes. Okay, I want to define for f here. Remember its equivalence class to the power p is integral mod f to the power p to the power 1 by p. So only thing remains to be shown is triangle inequality. Okay, that is known as Minkowski inequality. Okay, what does it say is if f and g, did I have not proved oh my gosh, yeah, okay, yeah. So let us go back. Young's inequality proves what is known as Hölder's inequality. H, this is umlaut. Hölder's inequality. It is not read as Hölder, it is read as Hölder. Okay, it's something to do with the German language or something. Okay, so we want to get Hölder's inequality. H-O umlaut L-D-R. What does it says is f and g be measurable functions. Be measurable functions on x, b, mu. Okay, so it may be real valued, complex valued, or extended real valued, I don't care. Alright, then what it tries to say is integral of mod of g d mu over x is less than or equal to LP norm of f into LQ norm of g. Okay, there are a few things which one has to notice. Okay, the first thing is, suppose my p is 2, then q is 2, right? Then what does it say? Mod of g is less than or equal to mod of 2 and L2 norm of f into L2 norm of g, right? This is the analog of Cauchy Schwarz inequality, right? What does it say? If a equal to a1 to an is in Cn or Rn, b equal to similarly in Cn or Rn, then a dot b modulus is less than or equal to norm a norm b, right? But notice that if I look at mod a as a vector which is mod a1 mod an, then norm of a is same as norm of this new vector mod a. Therefore what I have is a dot b modulus is less than or equal to mod a dot mod b, okay, is less than or equal to norm a into norm b. This is a dot product, that is mod a1 times mod b1 plus etc plus mod an times mod bn is less than or equal to L2 norm of a, the usual standard Euclidean norm. Okay, this is analog. Okay, that's the first thing. Second thing, this is what many people miss, even I have seen many experts missing. Okay, to do Hölder's inequality, I am not assuming, let me write this. Okay, whatever we will say is, if suppose f is not in LP, then suppose f is not in LP, what does it mean? That means LP now must be infinity, because mod f to the power p is not integrable. Notice that I can integrate any non-negative measurable function. Okay, if this is not integrable, simply means it has to be plus infinity, right? Now there are two cases. Suppose g, either norm of LQ norm of g is 0, in this case infinity into 0, right? In that case I have q equal to infinity into 0, which is 0. Now since this is 0, that means g is 0 almost everywhere. Therefore fg is 0 almost everywhere. Therefore this is 0. Therefore this is true. And simply interchange g, you get it, right? Therefore the interesting case occurs only if okay. And the third observation is, what is mod fg? I'm assuming simply fg and measurable, right? It says I want to estimate. Think of this, I want to estimate. Then it says this will be this. This I get an estimate. See, it may happen my f may not be in LP. It may happen g is in LP and f is in LQ. In that case, okay, I get an estimate, namely this is less than or equal to mod f LQ norm of f into LP norm of g. You understand? So don't presume f has to be in LP, g has to be in LQ. Is that clear? Right. Now I will finish the proof. With that I will stop. So let A equal to f of x. So remember, I am assuming f and g are finite everywhere. Okay. Otherwise, only on the for all x in the not in the exceptional point, I am looking at this. Divide by norm LP norm of f, and B equal to modulus gx and LQ norm of g. So this is the only trick you have to remember. Okay. Then therefore, by Young's inequality, AB is less than or equal to a to the power p by p plus a to the power q by b to the power q by b to the power q by q. That means what do I have? I have fx into gx modulus by norm of LP norm of f into LP norm of LQ norm of g. That's less than or equal to mod fx to the power p by LP norm of f to the power p plus LQ norm of g to the power q. Is that right? So if I integrate, I have mod fx gx, okay, over x, and this is a common, and okay, LP norm of f into LQ norm of g is less than or equal to, now when I integrate, this is a constant, this comes out 1 by norm of f p to the power p. There is also 1 by p, right? I forgot, because that is going to be crucial. Okay, right? And this into 1 by p. So less than or equal to 1 by p into 1 by LP norm f to the power p into mod f to the power p. Okay, this is nothing other than LP norm of f to the power p. Similarly, I have 1 by q into 1 by LQ norm of q to the power q into integral mod g to the power q, which is this. It gets 1. Therefore, what I get is 1 here. Right? Therefore, what I have is mod f g, transfer this to the other side, is less than or equal to LP norm of f into LQ norm of g. Okay. So Hölder's inequality. Remember, it's not Hölder. This O is there is called umlaut. This is called umlaut with O. It's almost pronounced as A sound, Hölder's inequality, but don't trust me. Okay. H-O-O-L-D, Hölder's inequality is proved. So I will stop here. Please go through this. From this we will introduce, this is the analog of Cauchy Schwarz inequality. In fact, it is Cauchy Schwarz inequality if n equal to p equal to q equal to 2. Okay, I'll resume that in the next lecture, and I will prove Minkowski inequality and hence show that this LP norm is a norm. Okay, right? And then with respect to the norm, LP is complete. Okay, that will be the end of the course on measure theory. Okay, stay tuned. I hope you like today's thing. There is a lot of work going on. Okay, and please go through it, try to understand and forget it. Okay, that thinking is good enough for you to recreate anytime, or to learn from books or from class notes, or to enjoy mathematics. It also to help you how to use measure theory, integration, etc. in your higher courses. Okay. Take care. Thank you. We will meet again.